Thanks to the organizers for inviting me. So I'm going to talk about how one can design fast spectral algorithms using a very classical area in analysis called approximation theory. So let me mention that this is based on a monograph with Sushant Sachdeva, who's right now a postdoc of Dan. And let me tell you very quickly what the goal would be. So the starting point is that many algorithms, as you probably have seen in the workshop so far, rely on our ability to compute approximations to certain matrix function times vectors. Okay, so the kind of things that probably you have seen are when you could solve a system of equations, in particular when A is a graph Laplacian, then this primitive has been used quite a lot already, and as we all know. Another primitive that a couple of talks mentioned is this matrix exponential times a vector. So again, if A is a graph Laplacian, then this corresponds to what is called the heat kernel, and it corresponds to a continuous time random walk in the graph. And I mean, these probably are very basic things that one would like to compute. And here again, if you want to keep in mind, you can think of A as the random walk matrix of a graph, and all this does is computes the distribution after S steps. So if you start with some charges on vertices, then A to the S computes the distribution of these charges after S steps. And among other applications of these methods are to sparse S-cut and other cut problems where the algorithms look at the top eigenvectors and eigenvalues of this graph. So we would like to understand how to speed these things up, speed these computations up. And the main kind of message of this talk would be that very often one could reduce the number of, so one could reduce these problems to a computation where all you are doing is doing matrix vector multiplications and a rather small number of times. Okay, so the matrix that often shows up is not necessarily the matrix that you start with, but quite often it is the same matrix. And in particular, if you could compute matrix vector products with for A, then you can also do that typically with the kind of matrices B that arrive here. Okay, so this makes them very attractive for algorithm design, because then you essentially reduce the problems to the number of these calls times the sparsity, or the time it takes to multiply the given matrix to a vector. And not only are these theoretically nice, practically, when data is stored outside, these result in really fast methods. And so this talk would go through trying to understand these reductions via a classical area analysis called approximation theory. And it turns out that often this is the right framework to study the complexity of these. How much can you speed these things up? So let me remind you of this area. So imagine that you are given a function which is, let's say, continuous, and what you're also given is an interval. So you're given an interval and a function, and what you would like is to find an approximation to this function in this interval. Okay, so for instance, here is this red curve, which is the function, and the green curve is a polynomial, or could be a polynomial, which is trying to approximate this function in the interval. Now here, there could be many notions of approximations that one could think of, and the notion of approximation that we would like is the infinity. So I'll define a word for it in a minute, but let me explain what is the quantity that we are trying to control. The quantity that we want to control is that this green curve is close to the red curve at every point in the interval. So you want to minimize the largest, the maximum distance between these two curves. So this is an infinity version of measuring distances. One could also ask for approximations in the L2 sense, where you're just minimizing the average distance. But as it will turn out that this is the right notion for us. So this is what analysts have been trying to do over hundreds of years. Let me formalize it a little bit and also talk about what are we looking for in this green curve. I mean, till now, we haven't really said anything about why are we doing this. So what we would like to have in this green curve or this function which we are using to approximate the given function is that it is simple, and by simple I mean, for this talk, it could be a low degree polynomial or a low degree rational function. Okay? So such approximations are called uniform approximations, and these were this line of research, this area was started by Chebyshev more than 150 years ago, and they ask for approximations of given functions by polynomials when the degree is specified. So sigma d is just a set of all polynomials of degree at most d, and when you're looking at the supremum of the error over the entire interval. Okay, and similarly, the quality, the quantity that we want to measure for a rational function is the degree of the larger of p and q. So p and q are both polynomials, and the cost that we will associate to it is the larger of the degree. So Chebyshev actually started this area in trying to improve the design for the steam engine, which was given by James Watt, and there the notion of uniform approximation came up very naturally, and since then it has many applications in many areas of mathematics and engineering. I'm not going to talk about it. Instead, I would bring your focus to the kind of functions that we are really interested in. So going back to the first slide, where I talked about the matrix functions, these are the corresponding scalar functions that we would be interested in. So for instance, you could think of a function which is just the simplest possible function, probably a monomial. So s is a positive integer, and you want to understand approximations to x to the s. Or the function e to the minus x. Or the function 1 by x. And each of these three functions will play a role in trying to develop fast algorithms for the three problems I mentioned in the first slide. And the kind of intervals that we would be interested in would be different for these three functions. So for x to the s, typically we would be interested in approximating it in minus 1, 1. E to the minus x in some interval which grows, think of n as a parameter which will grow, so some 0 to n. And 1 by x in the interval 0 to infinity. And for many of our applications, just good enough approximations will suffice, and we'll talk more about it. So let's go back to the matrix world and see how these things can actually help us. So as a simple example, we look at computing a to the s times v, where a is a symmetric matrix, and all eigenvalues are in minus 1, 1. So this you can actually ensure by scaling. So this is not a major restriction. The absolutely straightforward way to compute this, well, probably depends who you ask, but I mean, some people will actually try to compute this matrix, but I mean, the next level would be you just multiply the vector with the matrix A again and again until you get this thing, and this takes times order m times s. Okay, where m is the number of non-zero entries in A, or in particular the time it takes. You could replace m by the time it takes to multiply A with a vector. So often the matrix doesn't have to be sparse, and still you could you could compute these things faster. So that's what you would like to think of. Now suppose this very basic function x to the s can be approximated up to an error of delta over the entire interval by some polynomial which has degree d. Okay, so d is the degree of the polynomial, and the polynomial has this form. So it is given to you as a bunch of coefficients. Well, I mean, if you're seeing these things for the first time, you would say, okay, this is not possible. I mean, this is as simple as it gets. How can you reduce the degree here, right? But notice that we are allowing for some error, so it's not going to be something that, you know. So I mean, difficult to prove lower bounds here, and. So we'll come to what we can do with respect to the polynomial. But suppose you have such a polynomial and d of degree d, then the natural candidate approximation for computing this quantity would be to just plug this matrix in this polynomial and just multiply it with the vector v. Okay. This is what you would do. This is this is just a formal replacement of a scalar by a matrix. And now again you can check that the time to compute this quantity is order m times d, where m is the time it takes to compute one matrix vector multiplication with A, and d is the degree of your approximant. Okay? So this is why we chose d. This is why we chose to optimize on the degree when we were looking for approximating this monomial. So why is this a good approximation? Okay, this is where we will see why the notion of uniform approximation is the right one. So let's try to understand or analyze the error between what we gave as a candidate to this quantity. So this is what we suggested is what you should use as an approximation to a to the s times v. So imagine v is a unit vector. Okay, so if I want to bound this, it is sufficient to so you can write v in an eigenvector basis and an orthonormal basis, and it is sufficient to bound this error for every element of that basis. Okay, so A is symmetric, so the basis of choice would be the eigenvector basis for A, which is orthonormal. And the moment I plug in an eigenvector here, this inequality is nothing but querying this polynomial at that particular eigenvalue of the matrix. Right? We know that these matrices are simultaneously diagonalizable, so if I plug in an eigenvector here, what I'm going to get is lambda to the s and lambda summation ai lambda to the iai. Okay, and this is where we use this property that while we don't know exactly the eigenvalues of A, we do know that they are in this range -1 to 1. So but our approximation was close in the entire range, right? So if somehow you knew where the eigenvalues of A lied, then you could use this to get a good approximation to this quantity. Okay, so this, by a simple diagonalization argument for symmetric matrices, you are able to reduce the matrix problem to a scalar problem. So symmetry will be important here. And the closeness that you get is from the guarantee that this polynomial is close to the monomial. So now let's come back to the real question: how small can d be? For those of who have not seen this, any guesses?
I mean, it depends on delta.
First guess was
delta.
you would talk about it.
No, you guessed it right that time. Yeah.
You want it to be log 1 over delta? So,
That will be amazing.
but I don't. 1 over delta.
No, but I mean, that's really where that would be amazing. But it depends. I mean, I've asked this question to many people, and some people say D will be S. You can't do better than And some people just say d equal to constant. So there is a wide variety of optimism or pessimism that you can imagine. So it turns out, yeah, I mean, Ravi is right, it depends upon delta, of course. And it turns out the one answer to this question is square root of s. If I'm willing to kind of suppress the log 1 over delta term right now, then the answer is square root of s. And so the theorem is that for any integer s, any positive integer s, and for any delta, if I pick my degree to be square root s times log 1 over delta, then there is a polynomial of degree d which approximates the monomial x to the s within delta over the range minus 1, 1. Okay? So this result can explain many things actually, which some of which you may know, some of which you may not know. So for instance, so going back to simulating random walks, right? So imagine you are given a probability starting probability distribution, and you want to understand the s-step distribution. So you could do that now in m square root s time. Okay, as long as you're happy with some approximate answer. There is a famous method to solve linear system of equations called the conjugate gradient method. If all the eigenvalues of this matrix A are in the interval 0, 1, which in particular means it's symmetric and positive definite, then you can recover a very good solution to this in time, which is roughly the time it takes to do a matrix vector multiplication with A times square root of the condition number. So this square root comes out exactly because of this approximation. Similarly, you could go back to your method to use compute eigenvectors. So the most popular method is the so-called power method. And you could again speed it up. So typically you would never output the largest eigenvalue. You would output some approximation to it. So if you're happy with a number between, which is at least 1 minus delta times the largest eigenvalue, then you can again bring it down to m over root delta. So the traditional analysis of power method gets you m over delta. Okay? So these are three important results. I'm not going to talk about them. I would rather focus on showing you how to get such a polynomial. Because this is probably what you would not normally see. These methods, you probably know in some form or the other. You may not have seen them, as a more or less a direct corollary of this approximation. So the central player here is the Chebyshev polynomials. So there are many kinds of Chebyshev polynomials. I'm going to focus on a certain kinds of Chebyshev polynomials which can be recursively defined in the following way. So a Chebyshev polynomial is defined for every degree. So the constant Chebyshev polynomial is really just 1. The degree 1 Chebyshev polynomial is x, and subsequently you can define them recursively by this formula. So one way to parse this formula is the following, that they have this averaging property, okay, which says that if I look at the Chebyshev polynomial of degree d, then it arises essentially by taking an average of the two neighboring Chebyshev polynomials and dividing it by 1 by x. So you pick up a factor of x in this process. Okay? I mean, this just follows directly from this. I just shifted this term here and divided it by 2. And I just call d minus 1 and d minus 2 different things. So for people who have seen trigonometric polynomials, another way to define, which is an equivalent way to define Chebyshev polynomials, is that these are exactly the polynomials which will arise when you try to write down cos d theta as a polynomial in cos theta. Okay? So we all know that cos 2 theta is 2 cos square theta minus 1. Right? Am I right? So the Chebyshev polynomial corresponds to 2x squared minus 1. So in particular, this also implies a certain boundedness property of these Chebyshev polynomials, that they remain bounded in the interval minus 1, 1. This is important. Okay? I mean, this can be proved directly as well, but this is the cleanest way to see this. Okay, so let's get back to approximating the monomial. So here comes a probabilistic experiment. Which we will do. So imagine so remember, this S is the same S which appears in the monomial that we are trying to approximate. So let's imagine picking IID random variables, so identically and independently distributed, which are plus 1 and minus 1 with probability half, and let D sub S be the sum of these yi's. So another way to think of what D sub S is that imagine you start a random walk on a line of integers at 0, and then with probability half you go right, and with probability half you go left. So D sub S is your unsigned distance from the origin. Okay? Yeah, right? I mean, this is signed distance, sorry. That's what I meant. Yeah. Signed distance, yeah. So a basic Chernoff bound argument immediately implies that if you do this, then you are not very far from the origin, right? Your distance from the origin is not much more than square root S, right? And now exactly you can get the dependency on delta as well. So this is a tight result and can be proved easily by a Chernoff bound argument. Okay. So to relate this probabilistic process with Chebyshev polynomials, here is a simple observation. Okay, it's an equality. It says that imagine doing the following: that you toss these coins and then you see where you are. You look at the signed distance, and you pick up that Chebyshev polynomial corresponding to the signed distance. Now I haven't defined Chebyshev polynomials for negative integers, but you could just define them to be that for the positive integers. So t of minus d you could just define to be t of d. Okay? So if you do that and you look at the expected polynomial, then you recover exactly the monomial, x to the s. Okay? So here's a proof. It's by induction. Okay, it's really short. So the base case I will not do. Let me do the inductive part. So let's look at x to the s plus 1. So I will pull out one x from it and use induction to write x to the s as an expectation over these Chebyshev polynomials. And now I can pull x in and use that identity that they satisfy, this averaging property which I mentioned in the previous slide. So now I can write down TDS, x times TDS as the average of TDS plus 1 and TDS minus 1. So notice that this plus 1 is not with s, but it's with this random variable ds. But that is exactly the definition of TDS plus 1. So where you have chosen one more random variable. Okay, this is inequalities are always simple, right? So it's inequalities where we have to worry about. So here is an approximation to x to the s, which now is rather natural. That just define the polynomial to be the following polynomial. So what does this polynomial say? What does this what does this quantity say? That you again do a s-step random walk. You look at where you are, and only if you are at most a distance d, you output this polynomial, otherwise you just output 0. So you're cutting off the tail of this probability distribution. Okay, and the choice of D is exactly what was dictated by that, where basically it doesn't really matter when you can cut it off. Okay, yeah. And the proof that this is a good approximation is also rather straightforward. So let's try to understand the maximum error in the interval minus 1 of our polynomial and x to the s. So the way it is defined, if I remove this term, then I know that this is x to the s, this expectation. So the difference of PSD x and x to the s, what you recover is the complementary event, that what is the event that the distance is larger than d. Right? So I'm just taking the difference of these two polynomials using linearity of expectation. So what I get is exactly this event. And now I use the fact that these Chebyshev polynomials are bounded in minus 1, 1 by 1. So I can get rid of this thing completely. And so what I'm remain with is the expectation that I go a distance more than d of this event. But this is exactly the probability that I go a distance farther than d. But that by a choice of s is at most delta. Okay. So we crucially used the boundedness property of the Chebyshev polynomials here. This looks very simple, right? It's kind of hard to imagine that this sits at some of the most useful numerical and spectral methods that we use today. Okay, so now what have we learned from this method? So what we have learned, first of all, is that our intuition about how to approximate functions could be often wrong, because our first intent to, when we are given a function to approximate is to compute its Taylor expansion and truncate it at some point. Okay? So suppose you are a compulsive Taylor expander, right? So, but you could still do the following. So you compute your Taylor series, which is nothing but a polynomial, so there are these monomials in there. Just replace each monomial by this corresponding polynomial that we just computed.
Not by the Chebyshev polynomial, by the polynomial.
The polynomial that I defined. Yes, because it's in some sense you have a function which is the sum of functions. So I'm approximating each function, which in our case was just a monomial, right? And you actually can get quadratic improvement in the case when the Taylor series decays quite rapidly. So one such function for which you can get an approximation is the exponential. So you could do this. You could, we all know how to expand e to the minus x in Taylor series. It's 1 minus x plus x squared by 2 factorial minus x cubed by 3 factorial. So just go through this series up to a point that you like, and just replace each of these x to the I by the pi the corresponding pi. And actually this works. Okay, this does give you a degree which is quadratically better than what provably Taylor expansion can give you. Okay, so you get this b versus square root b gap.
So you're saying the Taylor series, if we take degree, to get constant delta, we would get degree b, or?
Yeah.
Okay.
Yeah. In applications in TCS, you would require delta to be 1 over polynomial in n, so you will pick up some log factors. Yeah.
What is this different from just doing the usual Chebyshev approximation right off the bat?
What is the Chebyshev approximation?
You use the roots of the Chebyshev polynomials to tell you what points to sample from your function, and then you interpolate by Legendre.
I think that is the L2 approximation.
That's L2.
Yeah. So infinity is a rather difficult problem. Yeah.
That's actually almost optimal infinity now.
Yeah. So under certain conditions, you can show that you can derive infinity approximations from L2 approximations. But it's not true universally. Yeah. But okay. So these are results which exist, right? This is not anything new, right? This is just a reinterpretation of many of these classical results. So,
Why can't you apply to itself? So now you have a
I
problem.
mean, like keep applying it again. That's great. I mean, that's no, it doesn't, because that's the next slide. Yeah. So I mean, it's.
Coefficients are presumably go up, yeah, maybe that's.
So no, so we can handle the coefficients as well. So that is not the issue, but it doesn't work. So there is a fundamental limit to this process. Yeah, and I'll come to that. But let me also, I mean, I think I slipped one thing, that this is the same square root improvement that you get in the Grover search in quantum, right? So people who are familiar with quantum, and this is exactly, I mean, you can prove Grover search also in this framework. I'm not going to do that. But since our motivation was things like solving semi-definite programs, and this multiplicative weight update method of Aurora and Kale required us to compute things like a matrix exponential times a vector, this does give improvements on running time for many semi-definite programming algorithms. Okay. And in particular, with Lorenzo and Sushant in 2012, we proved, not exactly via this way, but a related manner, that you could solve the graph partitioning problem of balanced separator in time which runs in m over root gamma, where gamma is the target conductance that you're looking at. So this is an improvement, and a similar result was gotten by Yuval Perez using very fancy technology of evolving sets, and this is very simple. Okay, so then comes Gary's question, right? How far can all this take us? So actually, not very far. So we can show, again, this probably many of these things were known somewhere in the literature. It's a 150-year-old literature. It's not easy to figure out what was known and what was not. But that aside, you can show that you can't improve on these square roots. So, I mean, I'll give you two illustrative examples that this monomial bound that I showed you can't be really improved beyond square root s. And if you wanted to approximate the exponential on 0 to b, then you can't get better than b. And actually, the proof of this relies on a very interesting theorem from approximation theory called Markov's theorem. So this is not the same Markov. Neither it's the same Markov, neither is the difficulty in the proof at all the same. So this is a much harder theorem to prove. I think it was the brother of the Markov that we know. And more interestingly, this was inspired by a problem that Mendeleev, who invented the periodic table, actually suggested to one of his colleagues. And the theorem says the following. It's an extremal statement which says that if you have a degree d polynomial which is bounded by 1 in the interval -1, 1, then its derivative cannot become arbitrarily high. The derivative is at most a d square. Okay. And this theorem almost immediately implies these lower bounds. And actually, Chebyshev polynomials are the tight examples for this statement. And actually, you can also consider higher derivative versions of this result. And again, Chebyshev polynomials are optimal from that. So how do we go beyond this? So there was a reason why I introduced rational approximations in the beginning, that we go beyond the world of polynomials and into the rather mysterious world of rational functions. Okay, let's see. And now Ravi's wishes will start coming true. Okay? So here is a result which says that if you have, we go back to, so from now on we focus on the exponential function. So if I look at this exponential function e to the minus x, and I want to approximate it by a rational function, so in particular it is just 1 over a polynomial of degree d over the entire interval 0 to infinity, I can get an error of at most 2 to the minus d. Okay, such a result cannot hold for polynomials. Polynomials blow up to infinity or minus infinity as as x goes to infinity or minus infinity. Okay? But the moment you allow me rational functions, I can get amazing results. So now, for instance, if I want delta error, the degree log 1 over delta suffices. And the polynomial is actually, maybe a die-hard Taylor expander will again discover it. We do nothing but just flip the function, take its Taylor series, and flip the Taylor series. Okay, that's all I've done here. So this is really the Taylor polynomial of degree d corresponding to the function e to the x. And I just look at the inverse. So this actually works. This could be a nice Math Olympiad problem that this works. And the proof is a clever inductive hypothesis. I'm not going to go into that, but I'll just bring your attention to the fact that there is absolutely no dependence on the length of the interval here. So the length of the interval in our theory settings, in algorithm settings, correspond to the norm of the matrices that we are looking at. So we work with positive semi-definite matrices. So the length of the interval corresponds to the norm. So from 0 to the norm of the matrix. And this can be rather large. So we are getting things which are independent of the norm. So I guess I already said this, that when in theory applications, delta is about 1 over poly n, so log n degree suffices, order log n degree suffices. Well, however, there is so this is your guess for, so if you wanted to compute this, you could try computing this. Okay? But this is a big problem. How do we compute this? So now we are in this world where we have reduced the problem to computing inverses. Well, that was coming, right? The moment you saw rational functions, you should have known that we would have to resort to matrix inversion. Right? But for this audience, it should not be a big surprise that there are fantastic results which do inversion in near linear time, right? So there is some hope, right? And that hope, at least when these matrices have nice structure, you would hope that you could invoke some of these Laplacian solvers or SGD solvers to be able to do this, right? And really get a m log n type of an algorithm for computing the matrix exponential. So let's see. So as I said, that so we are moving towards trying to understand to what extent we can invoke the Laplacian or SGD technology in these calculations. So what becomes natural is to understand the eigenvalues of this matrix, and in particular the roots of this polynomial. Okay. So one thing you could try to do is to you look at this polynomial. It's a polynomial which has a closed form, and you could factorize it. And instead of doing the inverse of the whole thing, now you have reduced the problem of inverting this and then taking products, right? So factorization helped us simplify the problem. So since our degree is log n, we just need to focus on computing these things. Okay. So imagine your matrix A was Laplacian or an SGD matrix. So then it becomes, the life would be great if all these beta i's are negative. Because if these are negative, then they only improve the SGD-ness, right? And then I could invoke these Laplacian solvers and at least for a large class of settings, be done with it. However, there is a problem. So for this polynomial, the roots are extremely well studied, and life is not as easy. So in fact, you can show all kinds of results about the roots of this polynomial. I don't want to go too much into it, but I can just tell you that you can try to wriggle your way around. It doesn't work. Okay, so there are many arguments that you could give, or many simple modifications that you could try to do. It doesn't work. Okay, And you could think about it. It's not too difficult. What would be nice, however, is if I could, instead of starting with this Taylor approximation, so once again Taylor approximation fails us, if we could come up with an approximation where the poles are all, whether the roots of that thing in the denominator or the poles of these rational functions are all negative. Because that's exactly the property that we are looking at. So this leads us into the world of trying to understand rational approximations where we have restrictions on the roots. Okay, so already rational approximations are difficult things to deal with. And now we want to be more ambitious, that we want conditions on the roots. Okay? But how about this? A smart undergrad, if you give them this problem, you say, you just don't know enough analysis. I know that 1 plus x by d to the minus d converges to e to the minus x. And it has this property that all roots are negative. So why not use this? Can anyone tell me why? Okay, so the short answer is that it doesn't converge fast enough. You can show that the convergence is slow. Okay, and I mean, in particular at x equal to 1, the error is quite large. In fact, you can even show something much stronger, that as long as you have 1 over a polynomial, you can't really do anything. Your error will be at least 1 over d square. Okay? So now what? Changwa?
Well, I can only guess you have to put something on top now.
Yeah. Or the next simple thing works. Just try to find a polynomial of this thing, which is the same as putting something on the top. So rather than looking at this guy here, you look at a polynomial of this 1 plus x by d, and this actually works. So this has all the properties that you need, except we don't know what the coefficients of this polynomial are, because this is proved via some kind of an convoluted existential type argument.
How did you find this reference?
Sorry?
How did you find this reference?
How did we find this reference? So that's actually an interesting story, I will tell you. So there was a paper by Arora and Kale which claimed this result actually, but I don't want to, this talk is being recorded, so. I don't want to get in trouble, yeah. Okay, so the coefficients is not really a problem. So we went through a proof of this, simplified some parts, and we could get reasonable bound on the coefficients, which actually works. I mean, you don't have to worry about these numbers precisely. Just remember that d will be like logarithmic, so these numbers are all small. Okay, in the eventual applications. However, in a couple of years ago with Lorenzo, we actually got a similar statement without knowing the coefficients. So there is yet another method called Lanchosh method, which I'm not going to talk about. But there is a way to get there is a way to extend just the existence guarantee of these approximations to algorithms without knowing the coefficients. It's much more hard work. And that's what we had to do, because at that point we were not able to figure out what the coefficients are. So in particular, so this is one of the main corollaries of this line of argument, which says that for SDD matrices you could compute very good approximations to the exp of minus a times a vector v in time which really depends very minimally on the norm of a. So the key point is to note that the dependence on the norm is log as opposed to square root, or trivially just the norm of a. Okay? And for applications to semi-definite programming, these numbers, the norms are bounded by polynomials, so this number is really some logarithmic. But all this was made possible by using the Spielman-Tang SGD solvers, and the great result of Saaf, Schoenhagen, Berger. And as a corollary, you could get, for instance, a linear time algorithm for graph partitioning problem. So before I showed a result where the dependence on the so there was a gamma, so it was m by root gamma, and now we could just even get rid of root gamma. And this is this SGD solvers that we used. Okay. So once you have such a result which uses such heavy machinery like the Laplacian solvers, the first question is, are these things really necessary? Are we being silly? Right? I mean, just because we can do this, are we doing this, or there is some really an inherent reason to well, at that time when we were writing the paper, we were in a hurry, so we didn't care. But after, we were worried, right, that maybe someone will say, oh, you don't need all this stuff. Maybe there is a direct way to do all this stuff. And the answer turns out that it is required. So there is a way to go the other way around. That if someone claims that they have the ability to compute matrix exponentials in the way this theorem guarantees, which depends on the norm logarithmically, let's say, then I could use this thing as a black box to obtain an inverter, a Laplacian solver. Okay. So this is a rather symbolful statement. I would like to bring your attention to two things. That so one is that you assume essentially that the condition number of the matrix is 1 by epsilon. This is what this thing is saying, and then there is an error parameter delta. So one could write A inverse as essentially a sum of matrix exponentials, where the number of terms in this is polylogarithmic in 1 over epsilon delta. So the log is very important. Okay, this log essentially implies that the number of calls to the exponential solver when you want to do Laplacian solving would be polylogarithmic. And the weights are not too large, so the error can be controlled. I mean, because this suggests a straightforward way to compute an approximation to A inverse times a vector, which is just compute this quantity here, right? But the errors will get multiplied by the weights, so you have to worry about how big the weights can be. But the weights are not so large. So this works out. I mean, if you could do this, then this works out. And the proof of this actually is somewhat complex. And I would encourage someone to try to come up with a simpler reason for this. But let me point out that naively, what you would try to do is use this identity. This is a basic identity which says that if you look at the function e to the minus xt dt, where t is the variable, and you integrate it from 0 to infinity, you get 1 by x. So we again go back to the scalar world. Okay? And our hope would be that if somehow we could discretize this integral, this is an integral after all, integral is nothing but a limit of some summations, right? The symbol is just a limit. So you could imagine that if you're allowed to discretize this thing, then you could just plug in the matrix and get a spectral approximation to A inverse using these things. So the straightforward discretization where you just chop 0 to infinity uniformly doesn't work. Okay. It will require a rather large number of terms, which is unacceptable.
You have to do it geometrically, right?
Yes. So the next thing actually works, which is to make this geometric substitution. and then do the uniform discretization in this. So first you elongate the space by exponentially, and then you do it. However, the proof is actually quite complex. It uses a whole bunch of results from analysis, in particular the Euler-Maclaurin formula, which requires us to control very high derivatives of this object, and in particular also uses certain estimates that come from the Riemann zeta function. And I would like to point out, this is, I mean, for people who have never seen Euler-Maclaurin formula and how it actually works, this is really, I mean, given that it was discovered maybe more than 150, 200 years ago, it's really one of the only methods I know which does a global error analysis. So, so the traditional strategy when you do things like this is to, you have a function whose integral you are trying to calculate. You chopped it up, and then you could do something like this. You could approximate this by rectangles, and then say, okay, upper bound the error here, upper bound the error here, upper bound the error here, and so on. That's what one way to do would be, right? But all that doesn't work. I mean, so the Euler-Maclaurin formula actually captures cancellations up to kth derivatives, and in that sense, it's really a very global analysis, but as a result, it requires you to be able to understand very high derivatives of the function. Okay, so.
But you could also view that sum as some funny combination of the, in the eigenspace or the eigenvalues, right? The eigenfunctions. I mean, because e to the t a.
Yeah.
You could sort of view that in the eigenspace.
Yeah, but that's exactly that's what we're doing here, right? So we prove the result in the scalar world, and then immediately by diagonalization move it up. But one point to note is that this does not require your matrix to be SGDA. This works for any positive definite matrix. Okay? And hence it suggests the following heuristic solver for positive definite matrix. Okay? So this is we don't know how to do this fast enough. I guess the best method I know is via conjugate gradient. So recall that your goal is you're given a positive definite matrix A, and your goal is to solve this system for the vector U. So you want to compute A inverse times U. So here is what you could try to do. Okay, this slide, I must warn you, is more speculative. So take everything with a grain of salt. So suppose you could write the matrix A as a sum of k matrices, which are in some sense simpler. So if you really want to have a concrete picture, think of A as a Laplacian, and think of A1 to AK as Laplacians of trees in the ground. So trees are easier than solving Laplacians, right? So that's what maybe you can think about. So when I do this, it immediately, I mean, by definition, e to the minus ta is e to the minus t times the sum of these guys. Okay? Nothing really happened. Now suppose magic happens, and k is small, and computing these guys, which, let's say, going back to our analogy with Laplacians, this is nothing but the exponential of the Laplacian of a tree. Okay. Times v is easier than computing e to the minus a times v. And also, let's say something like this holds. This kind of inequality, this kind of approximation definitely holds in the scalar world. So let's, for a moment, assume that this kind of thing holds in the matrix world as well. That you can write this matrix exponential as a product of these matrices. Okay?
That can be far off, right? I mean.
Yeah. So that's where there is a heuristic for solving. So I will come to it. Yeah.
Well, that's trace. Under trace, it's true.
No. He's right. So we come to that. Okay. So we come to that. So right now we are dreaming, right? It's like the last 5 minutes of the talk. We are allowed to. We are tired and we are dreaming. And so then you could just write down the following approximation, which is, so you use the theorem from the previous slide, okay, which told you that A inverse for any positive definite A could be written as a sum of. So the theorem said that A inverse is can be approximated by this thing. But then all we have done is opened up each of these e to the minus tj a, which was a1 to ak, and then we use this approximation. Okay, and this gives us this approximation to A inverse. Okay, so as a couple of more than a couple of people here observed, that this the problem here is the thing in the red. Really, everything else maybe you are, but this is just wrong. Okay, and this all graduate students should know, or even undergraduate students should know, that this holds only when all the matrices commute together. But this is a bit too much to hope for, to find a decomposition where all the matrices commute. Okay. So what Ravi said was this trace thing. So a version of this thing holds if you apply trace here, but then you get an inequality.
Didn't somebody mention Monomials formula?
Or least product.
I'm coming to that. That actually, Ravi meant Golden-Thomson. But Golden-Thomson also, Ravi, let me remind that it holds only for two matrices.
Right.
And there are classic wrong papers that appeared in Stock or Fox which used it for three matrices.
Not mine.
Not yours. Yeah. Okay. So, but as Gary said, right? So there is a theorem here, which is this Lie product formula from I think from physics or something like that. I don't know. But what it says is that this is morally true. Okay, that you could take your exponential and you just slow down the process. So you divide this by each of these bi's by p, and now you actually write it as a product, and now you do this thing p times. Okay. So if instead of something like this to be true, if approximations of this form, I mean, so this is definitely an approximation to this thing that you're trying to do. The question is, how big a p do you need, right? And hence a heuristic. Okay, so it's possible that for certain settings you could get p to be yeah.
There are papers in quantum computing on Hamiltonian simulation that have expressions like this, but that converge faster than the Lie product formula.
Yeah, so the naive analysis of Lie product form, I mean, the naive proof of this gives you a pretty bad bound on p.
But I mean, you can get things not that formula that converge better.
Oh, really?
Yeah.
I think I've seen such results which look at which expand in terms of this, and then the commutator, you know, the difference between the commuting and the anti-commuting terms, right? But yeah, this is just food for thought for to think about. I mean, probably this will not work, but I think it will be good to kind of rule it out formally. Okay.
Sorry, quick question.
Yeah.
So, I mean, one other thing you could do, Sankey's, I mean, another way to express the inverse, you take the characteristic polynomial and you get n terms, which is large, right? But then you take your approximations and replace by, so somehow with root n power, you should be able to do inverses, right?
Yeah, but root n, we can conjugate gradient already implies root n. So beating root n is the main problem here, right?
Yeah, root n is large, so.
Yeah, so root n we can do, right? But beating root n is really the point. That's what we want to do.
Nothing is already known for PSP?
I mean,
But the problem is
we have like experts in.
no, where you get things related to the condition number. If you don't want to have the condition number, it still depends on the dimension, not the square root. And the problem with just taking the characteristic polynomial and then substituting in your approximations is that would only work if like all the coefficients were positive or decreasing, or otherwise you're going to have issues with the cancellation. Like if you just approximate each coefficient, that is, I mean, each term, that's not good because they have cancellation in them. I think that's the issue anyway.
Oh, I think you're right. Only monomials are approximated this way,
Right.
and when you put coefficients, you better
Right.
worry about
Yeah.
Okay.
Yeah. Okay, so that's all I have to say about all this stuff. Let me conclude by just reminding you what happened. So we looked at this uniform or Chebyshev notion of approximation. This turns out to be the right notion for the kind of algorithmic applications to design spectral or numerical algorithms that are currently in the middle of revolutionizing fast algorithms. And one take home is that Taylor series is often not the best. In case you encounter a matrix functional like the logarithmic or something like that, that this is not the best thing that you should do. And as I said, that even many times, even if you just know the existence of good approximations, it's often enough for making these results work by combining it with what is called the Lanchosh method. So, well, as far as rational approximations are concerned, this is really a very bizarre area with almost no structure to it. And if you would like a challenge problem, here is a problem. So we saw that, so one interpretation of this matrix exponential result is that you could do continuous time random walks in time which doesn't depend on time, right? That's, if you wanted to do a t time continuous random walk, then you could really do it in m times logarithmically in t. Okay? Because t contributes to the norm of this matrix. Right, so we want to do e to the minus t times the Laplacian. So can we get such a result for our traditional random walk? The answer is I don't know, and I think this requires you to solve some approximation theory problem, which I don't know how to do. So you could try to follow the same framework, and I would conclude by just pointing out that looking at this heuristic that I presented. I would like to know personally if this cannot be leading to anywhere. And thank you very much.
We do have time for a question or two.
Yeah, John.
So I was just wondering if you've looked at the extent to which any or all of the approximation results that you're getting can be reproduced by looking at conformal maps. For example, the Euler negative x thing, what you would get if you, took a log to map the circle to the strip and then pulled back the Chebyshev polynomials.
So I think Yintat once suggested such a thing, right? So it doesn't work actually. We tried it.
It doesn't work for your challenging problem, but it works for your...
It works for many things, but it doesn't really work for this.
Does it work for, does it give an explicit answer for e to the negative x?
I don't think so.
Well, thanks again.
Thank you.